Hi, I'm Maciej, and today we will talk about Git and how it works from the inside. Like, this presentation assumes that you have some basic knowledge of Git and its main concepts, like commits, branches, etc. So, let's get started. This is me from 5 years ago, and at that time I had been using Git for 5 years. And I kind of understood how it worked, and I had no problem with simple operations. But when problems or some complications came up, I had no idea what was happening or how to fix it. And I felt stuck and frustrated. And I started wondering if there was something wrong with me. Like, I had been using Git for 5 years, and yet whenever something went wrong, I couldn't figure it out what was going on or how to solve it. And when I searched online to see if I was alone in this feeling, I found that many people had the same experience. They also thought Git was weird, hard, or not intuitive. Like, I tried learning Git from many tutorials on the internet, but all of them explained Git in a very general way, like using some abstract concepts without going into detail about how things work or where they come from. So, a year ago, I decided, enough. I locked myself in a room for a month, and I decided that I didn't come out until I understood how Git really works. Like, I went through the documentations chapter by chapter, sometimes even diving into Git source code to make sure I got it. And I took a lot of notes, I did a lot of experiments, and I finally managed to understand how Git really works. And I've come to two conclusions. The first one is using CLI. Like, you have to throw away your graphical user interfaces and start using Git from the CLI. Like, understand those bare metal Git, like using those commands, because it's really helpful. And the second thing is to actually dive deep into what's inside the .git directory. This is like where all that magic happens and all that crazy stuff goes on. And if you don't know what's .git directory, so in this example, I've created a directory. I initialized a Git repository with a branch main. And as you can see, with the ls command, there is a hidden directory. So when we are creating a repository, we are creating a hidden directory called .git, and this is where all that Git holds its stuff. So right now, I think with understanding of those two both things, I think it is not that hard. It's actually very useful and very helpful. And let's talk about it. So let's start with some basics. In order to start talking about Git, we have to understand what are hash functions, especially what is SHA-1 function. Because probably you're familiar with it, but I have to mention it because this is like the core fundamental of Git. It's a function implemented in most of programming languages and systems, which takes any input, which is file, document, photo, or PDF, and as the output, we're getting a unique 40-character string of letters and numbers. And what's important, for every different input, we're always getting different output. So this is like, without the hash functions, Git does not even exist. The second thing, if we will think about Git core, if we will forget about those concepts like remotes, branches, commits, Git is just a very big key value store. What does it mean? Like, the keys are the calculated hash functions based on the file contents, and the values are the file content. So we should start thinking of Git about like it's just a big key value store. Like it's like a database which lives inside that .git hidden directory. And what's inside that .git directory, you can see on the right that there are a bunch of files and directories, and we won't have time to cover all of them, but we will focus on the most important. And the most important are the objects directory, the refs directory, the head file, and the index file. So let's go to we will start with objects. Everything in Git is expressed with one of these 4 types of internal objects. These are blobs, trees, commits, and tags. Everything in Git is expressed with one of these 4. And if you list the Git objects directory, we can see that there are directories and there are files. The directories starts with 2 characters, and the files are the 38 characters. So combined, there are 40 characters. So we might notice that these are the hash outputs, and Git stores it in this kind of way. This is one of its optimizations. And let's start with blobs. So each file in our working directory, which may be our code, can be expressed as a blobs. So we have a file in our directory, in our working directory, Git performs some magic underneath, and it becomes a blob. And we can think of blobs as a generic piece of content. So we can basically, everything from our directory, like it may be text files, it may be videos, photos, PDFs, our code, can be stored inside that directory as a blob. And it will be internally in Git expressed as a blob. And if we will try to view the content of one of those files inside the Git objects, as a output we will get some random characters. And why? Let's get step by step how the file becomes a Git object. So right here we have some file. Let's call it a Ruby file. And what in the next step Git does is it takes the file content and it attaches at the beginning of that file content some special Git header. So then we have a combination of the header and the file content. These two are like concatenated like a strings, and it then goes to a compression. Git uses compression, lossless compression called deflate, and on the input we are getting that file content plus a header, and as a output we get compressed bytes. Then from those compressed bytes we are calculating a hash function using the SHA-1 algorithm, and then Git creates a new file, and that file name is a hash output. So this 40 character unique string of characters, and the file content is that compressed content. So those those bytes which are the result of the deflate compression method, and that new file is then saved to the Git objects. And that's why we cannot view the content of the file directly, because these are the compressed bytes from the deflate method. And let's demystify what's the blob header. It's just a text which is always structured in the same way. So we have the object type, a white space, a size of content in bytes, and then a null terminator. So this text is concatenated at the beginning with our file content. And take a look at the example. So we have our file content. Let's just type some random words. As you can see, this is our blob header and the content. So this is our header, and here our content grows. And what we can notice there is first of many Git optimizations, which is compressing. I cannot copy and paste. I don't know why, but when our content grows, so bytes grows, compressed blob does not grow as the uncompressed. So we're actually saving space by compressing it, and for each input we're getting different output. So this is like a live version of how blob is created, and then you will be able to test it by yourself. I will share with you the link with the presentation. So for the next examples we will use this file. Like, it doesn't matter what the file is, it's just for the example purposes. And now I will show you some Git internal commands, because in Git we have commands called plumbing commands and porcelain commands. Porcelain commands are those top-level commands which we are using on regular daily basis, like the git add, git commit, git status. But also when we are typing those commands and executing them, Git internally uses commands called plumbing commands, some like those internal low-level commands, and Git hash object is one of them, and it's used, for example, when we are creating the commits. So take a look at this example. We have a git hash object command, and we are passing a file to that command, and on the output we are getting a calculated hash by a git. And with -w parameter, we can actually save by ourselves that file to a git objects directory, because that previous command only returns it to the standard output, but this will save it. So we will perform the command like the git hash object -w and our file from the previous example, and we can see that this file actually landed here inside the git objects. And to view that file, we are not using the regular cat from Linux, but we will be using the cat file with the -p parameter. So we are passing our hash to that command, and Git decompresses this, removes the header, and returns to the standard output the content of the file. We can also use the -t parameter, and we can also pass them our hash and get a type. As I mentioned, there are 4 types, so we can always check what type of the object we're dealing with. In this case, this is a blob because this is just a file. And I really strongly recommend using that command on every file, not every file, but every hash, and also every ref. This is a spoiler, but you can just, if you are learning Git, just you can use some hashes, some tags, branches, just paste it and see what's inside. It's really helpful, and I'm still using it to nowadays. Okay, so we've covered blobs, so how our files are stored inside the Git, and now we will talk about commits. When I were learning about commits, it's most of the time in that tutorials explained as a snapshot of a project at a given time. And basically it's true. As a concept, it's true, but what commit actually is like internally. So, okay, in this graphic we have a project, so Git does some magic and it becomes a commit. A commit is a regular text file, which is always with the same structure. So we have a bunch of headers, a new line, and a commit message. It's similar to HTTP header. So, with the cat file command, I've passed a commit, which was created, and what headers we can see. There are 3 object, and 3, we will talk about 3 later, but 3 represents our working directory. It's stored to use the directories and files. We have a parent. Parent, it means that the previous commit, and Git always stores reference to a previous commit, which is parent commit, and hash to that commit. We have an author and a committer, so someone who did the commit, and the committer may be, for example, a GitHub when it creates a pull request and creates merge request after pull request. And we have our commit message. And this is a text file, this commit, which is saved inside the Git objects directory. We have a merge commit, and merge commit is a type of commit which has multiple parents. It can have 1, 2, or just n parents. It doesn't matter how many. And we have a special type of commit, which is commit without parent, and this is the first commit in our repository, or other calls them a Genesis commit. And the commit is created in the same way as the blob, because we're taking a commit, which is our text file. Git adds a special header, it goes to compression, it calculates the hash, it creates a file name with that compressed bytes and with calculated hash, and then it's write to the Git objects. But we have a problem. How do we store directories, and how about missing file names? Because when we are creating a blobs, we are replacing the file name with the calculated hash. And that's why there's a third type of the Git objects, and it's called a tree. So when we're creating a commit, we are creating a tree object. And tree object is a combination of other blobs and trees, and we are using it to reflect a project file structure. And it's just a kind of probably almost the same as Unix directory, which we are listing using the ls command. So again, with the cat file command -p, we can pass a tree object from our commit, and we can see that we have list of files. These are some access rights, the type of the object, because Git creates recursively other tree objects for other directories until we have only blobs inside our directory. And these tree files are also the text files, which are saved in the Git objects. And every Git object is saved in the same way with the same flow, and the only difference is with the name inside the header, so with the object type in the header. So yeah, with this knowledge, we know how commits are created, how directories are stored, how our files are represented inside it, and like there's no more magic. Like this is probably the deepest level which we can go. Also, we can go to the source code, but I don't recommend it because it's really complicated. But this kind of understanding is really enough to understand what's going on and to solve most of the problems, because we know how our working directory is stored and how commits are linked together. So we can see that how our Git graph actually behaves. And when we are talking about Git graph, we will move further to branches. And when I was learning branches, it was probably one of the most confusing thing, because when I was learning branches from the tutorials, from the online videos, like the branch is always expressed as like this development line, which is like the colorful metro line. The dots are connected with each other, and that's cool. But it's okay as a concept. Like branch is like an independent development branch. It's okay, but technically, branch is something different. Branch is just a text file, which the branch name is the name of that text file, and the content is the commit to which that branch points on. So the file content is that branch, and that's it. It was for me that like, what? Like it's. I thought that branch is something more, but branch is just a named reference. We have to think about branches as pointers, which some labels attached to a commit, which moves forward with each commit, and we can also move that label freely in our Git graph. And that's it. It was eye-opening for me because it means that our branches are not that complicated. And branches are stored in the refs directory, into the Git refs directory. And there are 3 subdirectories: heads, which stores local branches; remotes, which stores remote branches; and tags, which store tags. Probably we won't be talking about tags because we don't have time for it, but I can spoiler you that tags also behaves like refs. So yeah, the heads are local branches, so we have a file called master, which is our master branch, and the content of the file is the commit on which the master branch points on. We have the remotes, so the remote head and the remote master, they are also stored locally but updated only by Git. We have a head, and head means that head tells you on which branch we are currently on. And technically head is a file called head, and the file content is the ref, the colon, and relative path to which branch we are actually on. And that's it. And the other part, which was also some kind of like one of those WTFs for me, is when I was trying to use some Git graphical user interfaces and trying to visualize the Git tree. And I was wondering why in almost every tool the Git tree looks different. And when I'm performing some Git merging or manipulating with those branches, those colors actually start swapping and it becomes a mess. And it was very frustrating for me. And when I started digging why, what's the answer to this question, like it's like what I said previously, like a branch is a only named reference to a commit and that's it. Like those programs always try to guess where the branch starts and where the branch ends. Also, Git does not store information about the starting point and the ending point of the branch. It tries to guess it, trying to find the newest common ancestor. So that's like the answer to this. When we are talking about branches and about our Git graph, we have to talk about these two terms, about reachability and about dangling objects, because these terms are very important. Take a look at this Git graph. We have a tree. For example, we type the git log command and this is the output. When we have a branch which points on a commit, in this case we have a feature branch which points on this commit. So this commit and all parents will be reachable. So it means these commits are visible in a git log, they are visible in a git graph, and they will never disappear. So it means they are reachable. We will be creating new commits, the branch will move, and the new commits on the branch will be reachable. But take a look at this example. We have a master branch, and we are currently on it because the head is pointing to it. And we decided that we want to get back 3 steps. We want to take 3 steps back. So we type the git reset hard and tilde3 command, and bam, we are 3 commits back. And what was eye-opening for me is I always thought that in this kind of operation, these commits will disappear, like they will be deleted. But they are not deleted. Like they will always stay in the same place in that order in which they were created in our Git graph, but they will become dangling objects. They will become unreachable because only reachable commits are these which have a branch which points on them and all previous commits. These are visible. These are no longer visible and are becoming dangling objects, but they won't go anywhere. They will stay there as they are. So there aren't any situations in Git like my commits disappeared. No, they probably became unreachable. And there's a situation called a detached head. So we are performing the checkout directly on a commit. So, like when you did this, you probably noticed that Git throws that output that if you will create a new commit, it won't be visible in history and it won't be saved. So what does it mean? In this situation, we have a head which points to this 3fp commit, and we've created a new commit. And it's exactly what I've been talking about, these dangling objects and unreachable and dangling objects, because that newly created object does not have any branch which points on. Like there must be a branch. It can't be a head, and it means that this commit, even if it's created and it's in our git log, like we cannot see it from the git log or from any GUI tool. But there's one very useful command when we are dealing with those unreachable and reachable commits, and it's called git reflog. And git reflog is actually aliased for git log with some parameters, and it's a history on how our head was moving between branches or between commits, or what actions were taken in our Git graph. So in this example, when we've checked out on this commit 3fpo, we will get a entry that we've checked to this hash. When we've created a new commit, we will also get that information here that we've checked out at some point of time to that commit. And that's useful information because even if those commits are unreachable, we can still gain that hash from reflog, or we've maybe created a screenshot before, so we know that hash, and we can check out again on that commit, put a branch, and this commit will become, and all previous commits will become reachable again. So this is very useful information, that nothing in Git disappears and we can always like manipulate our graph freely, but we have to just know those hashes if you want to get back. So we can once again attach a branch as a pointer. But the sad part about git reflog is that it's stored only locally. So if you're resolving conflicts in Git by wiping your whole directory and cloning the Git repo again, you won't be able to use this information because it's stored only locally. Okay, so now let's talk why is Git smart at storing data. Because in this example, we have a second commit which created a tree object, and in that tree object we referenced a blob, which is a test.txt file with this SHA1. And in the third commit, we didn't change the content of this file. So the test.txt like stays as it is, and Git on each commit does not create a whole snapshot again of each file and directory, but it only stores changes relative to a previous commit. So it's important, especially when we are cherry picking, to think of commits as not like those snapshots, because technically it is a snapshot, but it's a set of changes instead of like the whole directory which we are trying to reference. So this is cool optimization because we are not duplicating the same files over and over again. And this is thanks to the hash functions. And if you once again take a look at our Git objects directory, we can see that there are many files. And this number of files can grow exponentially. And it's a bad situation because if you will try to push it on the remote repository, it's the same situation if you will try to push the node modules repository, which is a horrible idea because it will take years to push and you shouldn't do it. And how Git tries to optimize this operation is by creating pack files. This is optimization in Git, which tries to grab every Git object, so every of those small files inside the Git objects, and concatenate them, each one next to each other, to create one big pack file. And that one big pack file, like all of those files will become a big pack file, so it's easier to send one big file instead of 1,000 small files. And I've typed this command, git gc, and probably you're familiar with this output. If you're using Git on regular basis and you're using git push command, you've probably seen this thousands of times. But I didn't use the git push command. I've used the git gc, but the output is the same. And now we will talk about the garbage collector, because Git internally has a garbage collector, and that garbage collector does a few things. First of all, it deals with dangling objects. If you will get back to this graph, I said that these commits are in the graph, in the repository, but they are no longer visible. And garbage collector will always try to find all of these dangling objects, and if they are older than 90 days, like the 90 days is a default value in Git, then they will be deleted. Before that 90 days date, they will be always in the repository, and we will be able to, if we know the hashes, we can check out back on them and put a branch and they will be reachable again. The second thing which Git garbage collector does is creating a pack files. So it takes all that files and create like big pack files. And as we can see, after performing that command, all of those small files disappeared and two pack files were created. First with a pack extension, so this is where all our blobs were put and compressed. And the second is the index pack file. So Git garbage collector also creates a pack file index, and that pack file index is used to identify where in that big pack file each of the small files starts. So it holds a offset it holds those entries, and those entries are the offset, the hash of the object, and some CRC32 control sums. the same rule applies to refs. So refs can also grow inside the git refs directory. So instead of sending tons of small refs, a garbage collector creates a one packed refs file, and inside that file those refs are stored in a sorted order. And the last thing which garbage collector does is calculating deltas, and what those deltas are. Let's take a look at this example. In the first commit, we've created an image, which is just a big white square, which, for example, weighs 10 megabytes. And in the second commit, we've put only one single dot on that image. And that means that the content changed. And if the content changed, it means that the whole hash is changed also, and if the hash changed, we have to commit the whole 10 megabytes file again. So instead of storing those two files 10 megabytes each, Git will try to find that delta, so that the common part, and only store in the backfill that common part, and as a separate record try to only store that difference, so we are saving a lot of space. So that's very these are cool Git optimizations. And the last thing we will talk about is about those like the three trees, how Git documentation describes it. So it's a working directory, it's a index staging area, and a local repository. Like the working directory is the folder with our project where we hold our changes, and this is where we are. It's just a working directory where we are working with our project. The staging area, or also called index, is like a waiting room for files that will be included in the next commit. They are added with the git add command. And the local repository is like the final snapshot of our project, and just these are the objects actually stored inside the that git directory. And what was eye-opening for me is that the staging area, or other calls it index, like it isn't like a separate place where files are stored, but it's just a binary file located in this. It's a binary file in the location .git/index, and like the git index is the source of truth of our repository. And it stores like the entries about the files, their hashes, and some metadata. We cannot look it up like completely with cat command, or even with this ls files command which is used to view it, but we can only see part of this file. We can use different parameters to see different parts of this file, but this is like only to demonstrate to you that this file is important and what's inside it. So we have our current repository state, so which files are committed in a alphabetical order. And so yeah, I will just read it. Like the git index is updated when we are adding files. So when we are adding files to a staging area, there are new objects created just for the purpose to keep the current state. When we are adding or removing files from working directory, so it's also our index updated, so that source of truth is always up to date. And we are switching between branches, we are performing checkouts. This file also must be updated accordingly. And as you can see on this graphic from a GitHub blog, inside our repository we have some files, and when we are adding them to the index, we are actually storing them as a trees, combinations of trees and blobs, only just done for purpose of adding to index. When they are added to a repository, those objects are actually persisted in our git directory, and we are performing checkout. The working directory is updated accordingly as that index file. Our tree object, when we are creating a new commit, the tree object, which is that header inside our commit, the content is based on the index. It's done recursively. Also, when we are performing some diffs, it's also mostly based on the index file. And Also, it stores information about merge conflicts. Like when we have a merge conflict, there's like column full of zeros, but when there's a merge conflict, for example, there will be 1. I'm only showing to you that there are a lot of information, and Git always tries to find those information inside the index. Just give me a second. Okay, so I've been talking for past 40 minutes there about all those magical and technical things, and you may be thinking like, why do I need this knowledge if I'm using a graphical tool and it just works fine? And maybe you're right, but I think with this knowledge, Git stops being mystical. Like, no matter what problem I encounter, I know I will handle it, because I understand how it works. And what are the other benefits of trying to understand Git in that way I showed you? Like, the first thing is like it's stress-free development. Like really, Git stopped being scary and frightening, and I really like working with it. Even if there are some problems, I understand how it works and which solution I can try to apply to solve my problem. Like, I know I can freely manipulate on that Git graph, and I won't screw up anything. And the second thing is that it works in real life. Like, I prepared this presentation during the winter of this year while I was looking for a job, and I knew that starting work would be a real test whether this knowledge made sense. And I can confirm it really does. Like, I found a job in May as a Ruby on Rails developer, and this knowledge has been incredibly useful. Like, really, thanks to all of this stuff I show you, I haven't had any issues with Git for the past 6 months so far, and I haven't even had to ask any senior developer for help because there are some unsolvable mystical Git problems. So it's really, really helpful, and it works in real life as a real developer. Also, what became also no longer magical. Like, when I see the commit graphs, when I see branches, when I see that output from Git log, I know that there aren't anything scary because these are just commits connected with each other, and there are some branches pointing to it, so I can easily, freely manipulate that tree, and I can always restore to the state it was previously because of probably I've made a screenshot of those caches or I'm using a Git ref log, so it's actually kind of cool. The other thing, like, merging strategies also became they are no longer problematic. Like, when I'm performing the 3A merge or with the git merge --no fast forward command, so it means that I'm creating a new merge commit from 2 branches, and like, it's just a classic merge. When I'm performing a squash, for example, when merging a pull request on GitHub and I'm selecting like merge with squash, so it means that in a merge commit, there won't be 2 parent headers, which points to those branches. Like I said previously that the merge commit has 2 parents, but when performing a squash merge commit only has 1 parent, because we don't want to have that pointing back to the feature branch history. We want those commits from that feature branch to become unreachable, and if they're unreachable, we no longer see them in our history, so our history is cleaner. We have only all of those changes inside our merge commit. So this is very useful. When you're performing fast forward, we are not doing anything to the commits itself, but we are only updating the branch. So the branch points to other commit. We're just moving our label, and that's it. And with rebase, let's say we have a feature branch in our main branch, and Git tries to guess all which commits are on the feature branch and grabs them and puts them on top of that main branch. And that last commit from the feature branch now points to a new commit to a main branch, and it means that the parent changed. If the parent changed, the whole hash changed, and all hashes from that new branch which we put on a main branch have different hash. And this operation is dangerous when we are working on shared branches with other people, because rebase will change every commit shown, and you have to keep that in mind. Also, merge conflicts are no longer scary because First of all, when you type git status, it always shows you which files are conflicted and what to do. I know that at any time I can abort the merge, or if the merge failed or the merge is not looking like I would like to, I can just manipulate that tree with commands, like combination with some git reset commands and git reflog to find the previous, and I can start over and over again until I find that that the merge is successful. The other part, like cherry picking, like I said, like we have to think about commits as a set of changes, so I can just grab any commit from any point and put it anywhere, and it's just it. It's also a cool operation. I'm using it also in a job frequently. All of those paths are also no longer magical, because the dash selects parent header from the commit, and it means like if you perform the git cat file -p command, and there are a few headers, so it means that we are selecting like which header we are selecting, it means. But with the tilde, we are getting back a few commits, so it means that we are always grabbing the first parent header and getting one commit back, and again, and all of those relative paths are valid. What's interesting about git stash is when we are performing git stash, it internally creates like this illusion of stack, but these are just commits which git creates for us, and they looks like a stack, but these are just commits linked with each other. And you can also sometimes see it with some parameters in the git log output. When working with remote, it's also no longer scary, because this is like a recruitment question also, what's the difference between the git fetch and git pull. And when we are on a branch and we are performing git fetch, what we are doing is we are fetching all git objects and all git refs related to our current branch. And that's it. And also our remote branches are updated, and we have to merge our local branch and remote branch as we would like. Like there are many ways how to merge them. It's up to us. Like the git pull tries to also automatically perform the merge, but like the git fetch is just like download the current state, and we can now work on those commits like with any other. Like it's just not a problem anymore. And also that dangerous operation is also more safe, and you are internally more calm if you know what will happen to the repository tree, and like it's not that dangerous if you know what you are doing. And as the final words, I would like to mention that I'm not a pro, because even though I've said a lot of maybe interesting things, I hope so, but I mostly don't, for example, I don't remember many commands, because I think that's not the goal. Like the goal is to understand how Git works, and when there are some problems, I will sit down and try to figure it out, the solution, but I know what's going on, and most of the time there are a few solutions to the same problem, and the goal is to just solve it and to make sure that it works. And the last important thing which I would like to share with you is like Git does not replace communication with people, and you have to remember that no matter how good you are at Git, solutions must always be agreed upon together with other people. And like Git is just a tool, but it won't solve some like the communication problems, and that's the most important part about Git. The last thing, I've created during that sitting 1 month in the basement a tutorial which covers all of these topics which I've talked to you today. And if you would like to, you can check it out. You can see the examples, type them by yourselves, and once again go through details with those things which I've shown you. And I will share with you those links, and this is the link for presentation, and that's all. Thank you for listening.